And we're back to conclude 17-4, calculating heats of reaction. In this particular podcast, we're going to show you why the standard heats of formation equation, or Hess's law, actually works with standard heats of formation the way we performed it in the last problem. So here's the question. It says, calculate the standard heat of reaction for the following. Now remember, you have the delta H is going to equal the sum of the delta H's for the products minus the sum of the delta H's formation of the reactants. And so this is going to be this plus 2 of these minus this and this. So let's go ahead and take a look. We have the carbon dioxide. If you go on up there, the carbon dioxide is still negative 393.5. So we have 1 times a negative 393.5 plus we have 2 times the water. Scrolling up, the water is all the way down here at the bottom. Now you have liquid water and you have gaseous water. If you take a quick peek, we are actually forming gaseous water. The state of matter does really matter. So it's going to be negative 241.8. And so that is the sum of all the products. Now we're going to have to subtract that, or subtract from that, all of the reactants. Okay? Well, you have methane, which is CH4 gas. Let's go ahead and take a look at CH4. CH4 is right there, and it's a negative 74.86. So you have 1 times a negative 74.86. The 1 here is because you only have one of them out front here. And we're going to add the oxygen. Of course, the oxygen, though, is 0 because it's an element already in its standard state. So it's going to look something like that. And when you perform that calculation, what you get is a negative 802.24 kilojoules. Alright? So that would be the delta H for that particular reaction. So we can write this as delta H standard equals a negative 802.24 kilojoules. And so this is an exothermic process. Now, why does this work? All right. Let's go back to adding up the individual reactions so we can show you why this works. All right. Let's go ahead and color code this thing. So the first thing is we want to get that reaction on the, or that compound on the reactant side. So if I go from its standard enthalpy of formation, I'm going to write this backwards to get that on the left-hand side of my arrow. That's going to come from carbon, and it's going to come from hydrogen, and to balance the equation we need to put a 2 out front. The delta H for this reaction is going to be a positive 74.86. Now why is it going to be a positive value? Because when you reverse the reaction, the sign reverses. So the actual standard enthalpy of formation is a negative, and let's show you what that looks like again. If this thing is actually a negative, when you write it in the reverse, it becomes a positive. Alright? Let's continue on. In the next step, we're going to form carbon dioxide. Okay, we're going to form that. Well, in order to form CO2, we're going to take carbon in its standard state, which is of a graphite, but I guess we'll just assume that we know that, and react it with oxygen. It's balanced just as it is, and now we're forming carbon dioxide gas, and the delta H for that reaction, and again we'll consult our table, the formation of CO2 gas is still a negative 393.5. And since we're writing it in the forward reaction, we're going to leave it just as it is. So we have a negative 393.5 kilojoules. And then finally, for the water, if we want to form water, but remember our balanced equation calls for 2 waters, so we're going to need to run this thing twice, or just double everything. So this would be hydrogen gas plus oxygen gas, and to balance we put a 2 out front there, and now this thing is in fact balanced. And if you double check the water vapor, this thing is a negative 241.8, but you got to multiply that by 2 because you're forming 2 of them. So what I'm going to do is I'm going to say it's just a delta H equals 2 times a negative 241.8 kilojoules. And now if you add this thing up, watch what happens. The carbons cancel. The hydrogens cancel. And what you're left with is methane gas plus 2 oxygen gases producing CO2 gas plus 2 water vapors. And when you add all of these delta H's up, you get a negative delta H equaling a negative 802.24 kilojoules. So effectively what you're doing is exactly what we did when we originally took a look at Hess's law, where you're simply adding up a bunch of equations and adding up their delta H's. It's just that using this form of the equation when you're dealing with standard enthalpies of formation, it's just a shortcut way of doing all of this work. Now, if you don't have if you don't have thermodynamic data, you actually have to use the reactions that are given. If you're given a table with the thermodynamic data, you can just use that equation. Okay? All right. That concludes Chapter 17.